This third outcome is all about networks, the connections that let computers share data and resources with one another. We will look at the different types of network, the hardware that stitches them together, and the protocols, the agreed rules, that let very different devices actually understand each other. Let us start with the simplest idea. A network is just two or more devices connected so they can share things, whether that is files, a printer, or an internet connection. Networks quietly power almost everything: your home Wi-Fi, the office system, online banking, streaming, and the internet itself. Across this outcome, the key word to hold on to is protocol, which is nothing more mysterious than an agreed set of rules. Without shared rules, two devices simply cannot make sense of one another. One neat way to sort networks is by how far they reach. A personal area network spans just a few meters, like your phone linked to a pair of earbuds over Bluetooth. A local area network, a LAN, covers one site, a home, an office, or a school. A metropolitan area network stretches across a city or campus, and a wide area network, a WAN, reaches across a country or the whole globe, with the internet being the largest wide area network of all. Let us name the main types you will meet. A LAN covers a single site with high speed and local ownership, like an office network. A WAN connects sites over long distances, often using third-party links, the internet being the obvious example. A personal area network works over a very short range around one person, usually wireless, like a smartwatch talking to a phone. And a VPN, a virtual private network, carves a secure encrypted tunnel across a public network like the internet. Each type earns its keep in different ways. LANs give you fast, low-cost sharing of files, printers, and internet within one site. WANs join distant offices, so a company can operate as one, though they lean on external providers. Metropolitan networks link buildings across a city, such as a council or a university campus. And VPNs let staff work from home securely by encrypting their traffic over the public internet. A retail chain shows all of this at once: a LAN in each shop, a WAN back to head office, and VPNs for managers working remotely. But here is a distinction people muddle all the time: the internet versus the web. The internet is the global wide area network that links millions of smaller networks together. The World Wide Web is just one service running on top of it, the pages you view in a browser, and there are plenty of other services too: email, video calls, streaming, and file transfer. So the web is part of the internet, not the same thing as it, and your internet service provider is simply the company giving your home or business its connection to that global network. Let us build up a small network piece by piece. Every device needs a network interface card, a NIC, to join in at all. A switch connects the devices within a LAN and, cleverly, sends each piece of data only to the device it is meant for. A router then links that LAN out to other networks, such as the internet, and the signals themselves travel either along Ethernet cables or wirelessly over Wi-Fi. So the path runs from your device to the switch, to the router, and out to the wider internet. Let us put names to the main devices. A network interface card is the hardware that lets a single device connect, wired or wireless. A switch links devices on a LAN and forwards data only to the intended one, which keeps traffic efficient. A router directs data between different networks and connects your LAN to the internet. And a repeater boosts a weak signal so it can travel further, which is exactly what a Wi-Fi extender does around a large house. It is worth matching each device to its one-line job. A network interface card connects a single device to the network. A switch links devices within a LAN and steers traffic to the right one. A router joins networks together and routes data out to the internet. A proxy server sits between users and the internet, filtering and caching requests. A repeater regenerates a signal to extend its range, And a hybrid device combines several roles, which is what your home router really is: a router, a switch, and a Wi-Fi point all in one box. Should you go wired or wireless? Wired Ethernet uses cables to give fast, stable, and secure connections, which is ideal for fixed desktops and servers that never move. Wireless uses radio, Wi-Fi for local networks, Bluetooth for short-range gadgets, and mobile data like 4G and 5G over wide areas. As a rule, wired is faster and more reliable, while wireless is far more convenient and needs no cabling, and most homes just use a single hybrid box that acts as router, switch, and Wi-Fi access point together. Two words explain most of what people mean by a fast connection: bandwidth and latency. Bandwidth is how much data a link can carry each second, measured in megabits or gigabits per second, so more bandwidth means quicker transfers. Latency is the delay before data even starts to arrive, and low latency is what really matters for video calls and gaming, where a lag is instantly annoying. Performance also depends on how many people are sharing the link, interference on the Wi-Fi, and the quality of the cabling. A fiber connection gives high bandwidth and low latency, whereas old copper or weak Wi-Fi does not. Let us design a network for a 10-person office that needs shared files, a shared printer, and reliable internet. Each computer gets a network card and connects by Ethernet cable to a central switch for speed and reliability. That switch links to a router, which connects the office LAN out to the internet through the provider. Wi-Fi from the router then serves the laptops and phones, while the desktops stay comfortably wired, and a VPN lets anyone working from home reach the office files securely. Every choice here matches the hardware to the office's size, budget, and need for reliability. So what exactly is a protocol? It is an agreed set of rules that controls how data is formatted, sent, received, and checked. And both devices have to follow the same one, just as two people need a shared language to hold a conversation. Protocols cover things like addressing, error checking, speed, and security. When you visit a website, for instance, your browser and the server both follow the HTTP or HTTPS rules, which is why the page loads correctly rather than arriving as gibberish. The Internet runs on a family of protocols called TCP/IP, and it is organized in layers, each with its own job. IP handles addressing, working out where each packet of data should go, and routing it there. TCP breaks your data into packets and guarantees they arrive correctly and in the right order, reassembling them at the far end. There is also UDP, a faster, lighter alternative used for streaming and gaming, where a bit of speed matters more than perfect, flawless delivery. Let us meet the protocols you will bump into most. TCP/IP is the core, handling, addressing, and reliable delivery. HTTP loads web pages, and its secure encrypted cousin HTTPS protects things like online banking. FTP, the file transfer protocol, moves files up and down between machines. UDP carries fast streaming and gaming, and ICMP handles error messages and network tests, which is what the ping command quietly uses to check whether another machine is reachable. Wireless has its own set of protocols. Wi-Fi, technically the 802.11 standard, connects your devices to a LAN without any cables. Bluetooth links nearby gadgets like headphones, keyboards, and wearables. 4G and 5G carry mobile data across wide areas to phones and tablets. And HTTPS matters enormously because it encrypts your data, which is what that little padlock in the browser is telling you. Always prefer HTTPS and secure Wi-Fi with WPA2 or WPA3 whenever you are handling personal or payment details. Let us watch several protocols cooperate in one everyday moment, buying a book online over home Wi-Fi. First, Wi-Fi connects your laptop to the home router. Then TCP/IP addresses the data and delivers it reliably to the shop's server. HTTPS encrypts your card details so nobody can read them in transit. And the domain name system, DNS, quietly turns the shop's web address into the numeric address computers actually use. All of that happens in a fraction of a second, several protocols working together to complete one safe purchase. Finally, how does data find the right destination? An IP address is a number identifying a device on a network, something like 192.168.0.10, so data reaches the right place. A MAC address is a unique hardware address built into each network card, used within the local network. The domain name system, DNS, translates a friendly web address like bbc.co.uk into the IP address computers understand. And a port is a numbered channel that directs traffic to the right service, such as port 443 for HTTPS. Let us gather up Learning Outcome 3. A network connects devices to share data and resources, and we group networks by scale as personal, local, metropolitan, and wide area, with VPNs adding secure access. LANs give fast local sharing, WANs join distant sites, and VPNs encrypt traffic across the public internet. The hardware includes network cards, switches, routers, proxy servers, repeaters, and combined hybrid devices linked by Ethernet or Wi-Fi. And a protocol is simply an agreed set of rules, with TCP/IP underpinning the Internet and the likes of HTTP, HTTPS, FTP, UDP, and ICMP each doing their bit, while HTTPS keeps your data safe in transit. And that completes our look at how networks operate, from types and scale through the connecting hardware to the protocols that make communication possible. If you would like to explore further, the reading suggests top-down networking textbooks by authors like Kurose and Ross, along with the Cloudflare Learning Center for clear explanations and the National Cybersecurity Center for keeping home and business networks safe. There are a couple of neat case studies too: Janet, the UK's National Research and Education Network, and the web's big shift from HTTP to HTTPS after Let's Encrypt arrived in 2016. Do take a look, and remember, the assessment wants you to define a protocol first and then give named examples.